Okay, last thing I'm going to do today. It's going to take a while, but here it is. So remember when we said Carnot invented a cycle that he called the ideal cycle, and that cycle doesn't actually exist? This is the one cycle I want to talk about. Okay, so let's discuss an ideal cycle called Carnot cycle. So we are studying something from 1824. So Carnot cycle is the most efficient cycle for converting heat energy into useful work. Carnot cycle is the basis of nearly all cycles, whether they be steam engines, auto engines, car engines, or refrigerators. For people who are doing refrigeration, it's exactly the same. Okay, so what is it made up of? It is made up of a piston and cylinder device. It contains an ideal gas, and it has two reservoirs, one at TH and the other at TC, which is at higher temperature. Good. TH is called the source, and TC is called the sink. We also assume this is ideal. So it only takes QH from source and rejects all QC to sink. There are no losses. All processes are isothermal or adiabatic. Isothermal means delta T must be 0. Adiabatic means Q must be 0. So there are two isothermal steps and there are two adiabatic steps. Maximum energy that can be extracted in a Carnot cycle will be given by TH minus TC divided by TH, or 1 minus TC over TH. So this is the general, and I also want to talk to you about something that I'm going to write in a different color. Pick a color. No, I want it to be something that we can get rid of afterwards. Yellow. No, green is a good idea. So note, whatever I'm telling you is not true now. But this is the idea that Carnot based his cycle on. Are we ready? So put it in a box, put it in a different color. It's not true. So Carnot came from a time where the heat fluid theory was prevalent. So people believed in the heat fluid theory, that heat was a fluid that was exchanged between objects like a fluid would be exchanged between two objects. So Carnot thought that the steam engine, so Carnot thought that steam and water wheels had the same principle. Okay, so do you know what a water wheel is? What is a water wheel? When you drop water on a wheel, it turns, correct? The higher the dropped water is from, the more the turbines move, correct? So for a water wheel, may I write the potential energy as mgh2 minus mgh1? Yes? Carnot said that for my steam engine, I can write the same thing as TH minus TC, where the flowing liquid in one case was water and in the other case was heat. And he developed exactly this expression for maximum energy, TH minus TC divided by the heat we were putting in equal 1 minus TC over TH. As shown here. So the equation that he developed is absolutely perfectly fine. The concepts that he had on the back end are not. So we're still using Carnot's equation, but all of this in green is not right. Got it? Put it in a box, know where it comes from, know how wrong ideas could still develop perfectly reasonable explanations. And now we can move on. Are we good? So let's put this in the green box. This is what a cycle looks like. So this is our piston and cylinder contraption. These are the different volumes that our piston and cylinder will exist at. These two are isothermal processes. And process 2 and 3 and 1 and 4 are adiabatic processes. Okay, so let me discuss each point individually real quick. Don't think it's going to take us too long to do that. So let's start at point 1. So what is happening at point 1? At point 1, piston is at V1. System is in equilibrium with reservoir TH, which means what? What's the temperature at this point? Point 1. TH? Good. Okay, so then the system starts to move from point 1 to point 2. Is this gas expanding or contracting? Goes from V1 to V2. Gas is doing what? Expanding. So is the gas doing the work or is the work being done on the gas? Gas is doing work. It's an isothermal process. So that means temperature cannot change. So from the first law, what do I know? Delta U equals Q plus W. And the gas is doing the work, yes? So in order to keep the temperature the same, should I be forced to add heat to the system at this point to keep my temperature the same? Yes? So that means heat must be added. And we call that heat Q in. And how much heat must be added to the system? Corresponding to TH. Because TH is what needs to be maintained, right? So heat must be added at TH. Okay, so mathematically, may I write this as Q12 equals W12, where 12 is just the fact that I'm going from process 1 to 2, equal negative PdV or nRTH log of V2 over V1. Do I have to explain where this comes from? Okay, are we good? Then our system goes from point 2 to 3. So we're moving from point 2 to 3. What kind of a step is this? Adiabatic, right? What do I know about adiabatic steps? Q equals 0. I'm going from V2 to V3. So that means the temperature of my system goes from TH to TC. So gas, is it expanding or contracting? Expanding, right? From V2 to V3. So may I write for this, work 1, 2 will equal NCV T3 minus T2. Woohoo! Finally, we have useful work. Oh, sorry. Yes, it should be work 2 to 3. My bad. 2 to 3. Finally, useful work. At this point, it can change. It can turn the paddle wheel. Okay. Now at point 3, note what's going on. Your system can either go from 3, 2, 1 or from 3, 4, 1. Okay, note very carefully. Your system can either backtrack and go this way, or it can go this way. Can you think of a disadvantage or an advantage going either of those two ways? So let's say we're going the orange way.
Pressure changes rapidly.
Well, that's true. But what about the work?
0.
Will it be 0? Or do you have to provide it the work to make it go from TC to TH? The same amount of work, actually even more work, right? Yeah. To reverse it. So whatever work you got out, you have to put it back in order to go back the same way. So what's the advantage of your power plant? If you just keep running the power plant to run itself, right? So it is more advantageous to go from 3 to 4 and then back to 1, right? Because we do in a cycle, we have to, remember we said we start at point 1, we have to end at point 1. Okay. So at point 3, it chooses to go to point 4. When it goes from 3 to 4, what kind of a process is this? It is isothermal. What do I know about isothermal processes? Delta T equals 0. volume goes from V3 to V4. Is it a contraction? Yes? Is it contracting from 3 to 4? So that means work is done on the gas, which means I can rewrite this as Q34 equal minus nRTC log of V4 over V3. And at this point, heat Q34, which is also called QC, must be extracted. Do you see it? Do you see it? Do you see it? And the last step is going to be from 4 to 1. This is an adiabatic process. That means Q must be 0, which means you must provide external work to get the system back from point 4 to 1. And how much work should that be? 4 to 1 will be NCV negative T1 minus T4. And that is an ideal system. I want to quote Schrodinger here. He said, "Don't bother installing a Carnot engine in your car." Why do you think he said that? The reason why he said that, think about it. Carnot cycle has 2 adiabatic processes and 2 isothermal processes. When I started this discussion, I said, for ideal cases, I use the word quasi-static. What does that mean? That they occur almost statically, which in turn implies a long time, slowly. So what do you think isothermal processes, how long do you think isothermal processes take? A long time. So he said, don't bother installing a Carnot cycle in your engine or in your car. While it may increase your gas mileage, you will be passed on the highway by pedestrians.